right, let's get started. This is going to be the last lecture of the Causality class, so congrats on making it through. Unfortunately, we're only doing one lecture on causal representation learning, just with deadlines and stuff. It was easier to do that. We're going to cover kind of a broad range of material today and kind of give you a flavor of some of the stuff that's going on there. But it's definitely not comprehensive. None of this course has been, obviously, so hopefully this is all building a good foundation for y'all to go and read papers, read the literature on this, and feel free to contact me by email and ask about stuff if more comes up in the course of your research or classes or whatever. Always happy to talk about it. For those of you doing the PSET, the final PSET's due on Friday at 11:59. I said this last time, just shoot it to me by email. So if you remember from the first lecture, when I was giving an overview of the class, the kind of perspective I was taking on the three sections of the course was that we were starting off with policy evaluation, where we had a known causal graph, and implicitly, if we have a known causal graph that's over some variables, we're also going to know what those variables are. Then in the second section of the course, we talked about causal structure learning, where we didn't know the causal graph, but we did know the causal variables. So the whole goal there was we get like a data set measuring all of the causal variables. Can we figure out what the causal graph is, either from conditional independence constraints implied by the data, or we briefly talked a little bit about incorporating interventions, constraints from those interventions, as well as kind of some score-based methods where we would score the graph and pick the best scoring graph. And we talked about kind of sparsity and Chickering sequences as a way of kind of exploring the space of graphs. So finally, what we're ending on is causal representation learning, where we're going to assume both of these are unknown. And this is going to be a pretty hard problem, but this is a kind of problem that we're going to care about in a lot of applications. When you're actually starting to think about ties between causality and machine learning, well, in machine learning, what you're seeing, if you're thinking of like image classification, you're seeing pixels. And you're not saying like, oh, the pixel in the top left corner is causing the pixel next to it. What you think might be going on in kind of causal terms might be that there's some underlying abstract variables behind that. So the picture that I have in my head when I'm thinking about causal representation learning, this is certainly not the only picture, but this is kind of what my research has been on, so it's going to be what I'm talking about today, is that you have some causal model over some variables z that you don't get to see, say z1 through zd. And instead of seeing those, you see some kind of high-dimensional projection of that, or representation of that, which can be in a space with maybe many more coordinates. So with a 100 by 100 pixel image, like 10,000 coordinates, there might really be only a few latent concepts that are describing what you care about in the image. So for instance, what you might care about for like image classification in this latent space, you might be thinking, well, one of my variables, this might be like my label, could be dog or cat, and then some aspects of the image that if we like think about what's going in the world that generated this image in my data set would be, say, if it's a dog instead of a cat, maybe it's more likely to have a collar on. People are more likely to put collars on dogs. And if it's a cat instead of a dog, maybe it's more likely to have long whiskers. And you would think, I want to use my image classifier in different situations. So maybe I go to a city where people need to leash their cats for some reason. So all the cats are wearing collars. Well, you wouldn't want it to think like it's picking up on the collar variable and saying, okay, that's what it was using to signify whether it was a dog. So you kind of want to disentangle those and also understand kind of the causal relationships between these variables. Like if I put a collar on an animal, it doesn't turn it into a dog. For kind of a more like scientific or applied example, you might think about doing disease prediction or diagnosis. So you might think that I'm coming in and I'm seeing a patient that has some disease I don't know, but what I get to see is like an fMRI of their brain, as well as maybe some vital signs, so like blood pressure, stuff like that. And those are this kind of high-dimensional feature that I get to see, and what's like really driving it is some underlying biological process that I don't get to directly observe. Say maybe what their disease is, like whether or not they've had a stroke. A stroke can cause a lot of things to go on in the body after that, so there could be a stress response from the body. They could aspirate because their throat muscles aren't working as well as they used to before the stroke. And those could lead to things like low oxygenation that I might be able to directly observe in my data. So we're kind of thinking of things like this, where we have some high-dimensional output, and we want to find these latent variables. And I guess there's a few different approaches that we might take for that. So what are the parts of this model, right? There is the structural causal model over the z variables. There's the function that maps that structural causal model to what I observe. So I'm going to call that g, and that's going to be something that I'll refer to throughout as a mixing function. So one way to think about this map is that it's taking each of these kind of individually semantically meaningful components in the latent space, kind of mixing them up into components in the observed space. And then something that I'm not picturing here, but that is kind of implicit in the fact that we're using a structural causal model, is that we might also have interventions on the latent variables. So if we're thinking of looking at a data set, that's like having a separate data set where I've gone in and put colors on all of the animals. You could also think about this, and this is a little bit more common, in terms of kind of distribution shift or like sparse mechanism changes. Remember in the first lecture with structural causal models, we called interventions also mechanism changes. So this intervention doesn't have to be coming from specifically somebody going in and saying I'm going to perform an action on the system that's going to change it. It could just be I go from one city to a different city, and I think that that has kind of a sparse effect on how my structural causal model changes. And we can kind of get identifiability of this model in the latent space by putting restrictions on either of these two components, the structural causal model or the mixing function, or by introducing interventional data. So just to write that out, let's put possible approaches to identifiability of a latent DAG. So first, I said we could restrict the structural causal model For instance, something that goes back to the 90s is linear independent component analysis. And then there are more recent generalizations of independent component analysis. And that would say that I know ahead of time that the causal variables, the latent variables, are independent of each other. So really there's no causal structure. This is kind of like a degenerate case or a very special case. You could also think about, I have some known causal structure that I'm trying to match. This is not going to be something we're going to talk about too much today, because what we're really going to care about is like having an arbitrary causal structure and then trying to learn it. So our other two options are to restrict the mixing function. And that's an approach that's received a lot of attention in the last maybe 2 decades. We're going to talk about some of the fundamental concepts behind that. And then an approach that, at least to the best of my knowledge, has just started receiving attention more recently is incorporating interventional data. Right? And when we do one of these two approaches, we might have two goals kind of going along with the two parts that we have here. So the first goal I would say would be to recover the causal graph over Z. And the second goal would be to actually recover this mixing function G, or if it's invertible, recover its inverse. And this is going to be, this point's going to be a little bit of a difference between the two types of models that we're going to look at today. So I guess one of the more general setups is that we have x equal to g of z plus some noise. So let's call that noise nu to distinguish it from the epsilon variables that are going to be the exogenous noises for the causal variable z. So in general, we would call this a additive noise causal disentanglement model. And what you would want also here naturally would be that V, this noise variable, has a product distribution. So the noise on each of the coordinates of xi is going to be independent. One note is that, you know, this and kind of this picture all are kind of these models that are implicitly following the measurement assumption. And that is saying that, you know, X is not itself kind of involved in anything kind of causal, in terms of X is not causing the Z variables and the X variables are not causing each other. People do study those types of models as well, but, you know, maybe if we're thinking of like the image case, it's less applicable. You know, the pixels in the image are not causing the like latent variables in the real world, and they're not causing each other. They're kind of all just a function of the latent variables and then maybe we're getting some noise on top of that. And the special case where recovering G actually allows us to like perfectly invert each of our X samples. So there's no noise. We'll just call a deterministic version of this model. So one way to say that would just be nu equals 0 almost surely, or we could just drop the nu altogether and just write it as x equals g of z. And then, yeah, if that function is invertible, a new sample, if you give me a sample xm, then I can just put that into the inverse. So this would be like learning a function where I can put my image in and then get out what the associated latent variables are. Okay. If you don't have that, you'd get like a posterior distribution over what your z's are. Okay. And in this lecture, we're going to focus everything in the linear case. So this is, now there's two parts to this model, and we're going to have them both be linear. So we'll call a causal disentanglement model linear if first Z follows a linear structural causal model, if you don't remember, that was just saying that all the causal mechanisms are linear. So each variable is just a weighted sum of its parents plus some noise. And then second, the map from the latent variables to the observed variables is linear. So we can write G of Z is equal to some matrix G times Z. So this would be a matrix in RP times D. Okay. So one thing, just a silly example to kind of make it clear that this is even a harder problem than our kind of causal structure learning problem when we knew the variables. I'll show that you can't even recover this up to Markov equivalence. So there's generally, if you only have observational data, and you're not incorporating any interventions, and if you're not making any restrictions on the mixing, you can just recover a solution where all the z variables are independent. So that's going to be a generalization of this example, but I'll do it for just 2 nodes. So say if you have z1 is equal to epsilon1, and z2 is equal to a12 times z1 plus epsilon2. We can write that in matrix form as z equals, should be this, times epsilon1, epsilon2. Then if we have x equals G11, G12, G21, G22 times Z1, Z2. What's basically going to happen is we're just going to compose these. So we put the Z1, Z2, this expression in here. So we can just expand this out and write it as, so we're going to get the first row times there. We can get G11 plus G12, A12, G12, G21 plus G22 A12 G22, and then the epsilon 1, epsilon 2. Right? So we can just take x to be this linear function of the epsilon 1 and epsilon 2 variables, which are independent. So we had like z1 to z2. Those were both having epsilon 1 and epsilon 2 put into them. And then we had x1 and x2 that were both functions of z1 and z2. All of these are latent. And what we're doing is just forgetting about these z1, z2 variables and having the map from epsilon 1 and epsilon 2 be the composition of those two maps. Okay, so this is what's supposed to make it clear that we need to do at least one of these two things in order to get identifiability. So I guess first the idea of restricting G. I guess at the extreme level, if we restrict G to be the identity, then we're just back in the case of our normal causal structure learning with known causal variables, right? So a lot of the kind of, most intuitive versions of restrictions that we can place on G are kind of extensions of that idea of instead of restricting G to be the identity, maybe kind of restrict it to have the identity kind of buried somewhere in. And that is going to be what we're going to call a pure child assumption. Pure child is also sometimes called an anchor. And this is an observed variable. So some xi such that it only has one latent parent. This is also similar to proxies when we talked about proxies in the policy evaluation section of like we have a latent variable and we have like separate observations of it. We have variables that only depend on it. So it's an observed variable xi such that we could say the parents of xi just equal some zj. And the reason this is kind of similar to this identity case is if you look at this matrix, then if we're still in this linear case, then if we take the I coordinate for x and the j coordinate for z, then this is like the only non-zero entry in that matrix, because we're saying all the other parents of xi, or all the other zj's are not parents of xi, so all of these entries are 0 besides the zj entry. Okay. So an example of a model like that will actually show we can distinguish from other models would be if we have something like this, z1, z2, z3, and then say each of these has, say like x1, x2, this one has x3, x4, this one has x5, x6. And my goal with some of the math and results that we'll be developing in the next maybe 30 minutes is to show that we can distinguish this graph from the one that has the arrow there. Okay. So I'll come back to this in a minute and mark it up with some coefficients on those edges, and those are going to basically be coming from our mixing matrix G and our linear model in the latent space. So we're going to say that we're going to say that a linear structural causal model has weight matrix A. So this is going to be, we're going to be thinking about it being over our latent nodes. This is an RD by D. And this is going to be with causal graph G. So it's going to have, we're going to say it has weight matrix A, where Aij is equal to 0 unless I think the way that we want to do it is as we had in the model over there, we had an edge from Z1 to Z2, and then we had a non-zero entry in the 2, 1 coordinate. So this is non-zero if xj goes to xi. This is what happens if we take that matrix to be lower triangular. So we have aij equals 0 unless that weight is there, or unless that edge is there. And it's going to have exogenous variances. Sigma 1 squared through sigma p squared. And this is the case if, for all of the coordinates, we have that they're exactly that linear function of their parents. So xj and the parents of xi of Aj I xj plus epsilon I, where epsilon I is distributed, or I guess we want the whole vector of epsilons to be distributed such that its covariance matrix is this capital omega, and that capital omega is just going to be a diagonal matrix with each of those variances on it. So we're going to have capital omega equals a diagonal matrix. This should be another way to kind of rewrite this that is going to prove useful is to, instead of saying that we're basically just going to normalize these exogenous noise terms. So we're going to move their variances into this equation. So we'll have this. We need omega to the 1/2 here. And then this covariance of the epsilons is just going to be the identities. They're all going to be unit variants. Yep.
I'm looking at these notations. X is Z or X.
Sorry. Yeah, I was saying that I should be doing this over Z. So this should be Zi equals, change all of the x's to z's. Thank you. Good now?
I think it should be Ci to Cj if we're using co-effect.
Okay, in this case, we have Z1 to Z2, and then we have the 2-1 entry is non-zero. So I'm putting, this is because it's a lower triangular matrix, so it's going to be in the opposite order, unfortunately. Okay, so writing this out, this is like line by line. These are the causal mechanisms. We're defining each of those individually. We can also write this in matrix vector form. So then we would have Z equals A times Z plus sigma 1/2 epsilon. This should be the sigma I coordinate. Okay. I might be getting some transposes wrong, so definitely good to check. Tried to get them right, but it was flip-flopping. So if we take this matrix, this A, over to the other side, yeah, I do think this is supposed to be A transpose. If I take this over to the other side, and I will get I minus A transpose times Z. That I minus A transpose, so this is a general fact about matrices. If I have a, if I'm subtracting off a matrix which is strictly lower triangular from the identity matrix, then it's invertible. So in particular, I can write out this I minus A transpose inverse omega 1/2 epsilon. Yeah, this doesn't necessarily have to be lower triangular itself if we don't kind of impose an ordering of the labels in Z, but it would be upper triangular or lower triangular up to a permutation. In fact, we'll see that we might as well impose an ordering over our Z variables and make this lower triangular, because we can kind of get the same solution from relabeling. Yeah.
Why don't we have a constraint regarding the DAGness of A? Right, like
this is DAG.
Oh, this is DAG already.
Causal graph. This is particularly a DAG. Yeah.
And so the reason we don't worry about it's just weird. Z is equal to A transpose Z. And the reason this.
Yeah, so if you look at every individual line of this equation, none of the coordinates of Zi depend on itself.
Exactly.
But when we collect it into this equation, that part is no longer clear, and then this is, if I had no restrictions on this, this could have multiple solutions or no solutions. And the fact, like the going from this line to this line is exactly due to the fact that A is a DAG, that this is always going to have a unique solution, and it's going to be this. Yeah. Cool. Okay, so I might have gotten some detail wrong. This is how I have it in the notes, though. Let's go with this, and let's work on this equation. So what we're going to primarily care about is, because we can always think about the Gaussian case, right, where the all of the distribution is completely defined just in terms of its mean and covariance. So if these epsilons have mean 0, really, that just by linearity, C is going to have mean 0. The only thing really characterizing it is going to be its covariance. So let's look at what the covariance of this is. We can get the covariance of Z. If it's 0 mean, we just do the expected value of Z transpose. Okay, those terms here are not random. So by linearity of expectation, everything on that side is going to come out as I minus A transpose inverse sigma to the 1/2. And then we're going to get expected value of epsilon transpose. And then similarly on this side, the transpose of a diagonal matrix is just itself. And then we're going to get at the end times this I minus A inverse transpose. And then we said this is just the identity. So we can bring all of this together and get I minus A transpose inverse omega I minus A inverse transpose inverse transpose, and then these are going to cancel out. So this is just going to be I minus A inverse. Okay. Let me make it clear, because this is an equation that we're going to be building off of. So kind of something looks a little maybe difficult here, because we have the inverse of a matrix. That's generally going to be a hard thing to work with. Something that's going to be nice, because this is a DAG, is that this matrix is actually going to have a meaning in the DAG, and it's going to be kind of easily computable. So I'm not going to write down the definition of a directed path in a DAG, right? This is just a path where all of the edges are going in the same direction. There's no colliders, I guess, right? I will write down a notation, which is that Pg of xi, xj is going to be the set of all directed paths from xi to xj in G. And then if we have a path, so if we have some gamma, we can define the weight of that path as just the products of all of the individual edge weights along that path. So W gamma is equal to the product. So if the path, say, is of length m, this will be m equals 1 to m minus 1 of the weight a, whatever, gamma m to gamma m plus 1. Okay. And then the characterization of that inverse is that this is actually proposition 3 in the notes, so I'll skip ahead and then I'll come back to proposition 2, which we just used to prove proposition 3. So the ijth entry in this matrix is just the sum over all paths of the weights of those paths. So think of this I minus A inverse matrix as giving you the kind of total effects of each of the variables on each of the other variables. Variable xi on xj. It's all directed paths.
And what about the transpose?
No. Yeah. I'm pretty sure it's not. Okay, and this is a combination of two facts. So the first fact, which I'm calling proposition 2, is that the ijth entry of A raised to the kth power is the sum of all length k paths. I think I've done it again where I've been switching between x's and z's. So let's go back to z's. If we go back over to that board, I'll swap out whatever x's are over there for z's. But yeah, so this is going to be the sum of all length k paths from zi to zj. So I could just prove this in one line, but let's get some intuition first. What happens when you take the square of this matrix? So we're multiplying the ith row by the jth column, so I get A, I, U, A, U, J. So these are all length 2 paths. I'm summing over all nodes where I can put that U in between them, right? So if I had a K, I can do a similar thing, just write this as A to the K minus 1 IU. So it's the IUth entry of that, which by induction is going to be the sum of all paths of length k minus 1, and then I'm just considering adding one path to that. Okay? And then the relationship to I minus A inverse is essentially kind of a Taylor series. It's even easier to prove since we're in the case of DAGs. So in the case of DAGs, you can't get any paths of length longer than d, or else you would get a cycle. So in particular, A to the d plus 1 and all greater powers are equal to 0. So we just want to check that the inverse of I minus A is equal to the sum of all paths up to length k. So we just need to check that it, by this, is equal to sum from k equals 0 to d of a k. So, right, we just distribute and we get that this is k equals 0 to d. This is k equals 1 to d plus 1. And then all of the terms are going to cancel except for the first term of this guy, which is just a to the 0, which is the identity. So that's a nice basic fact about weighted graphs. And we're going to use that in combination with this expression for the covariance to come up with a formula for the individual terms of the covariance matrix. Okay. So in particular, if we have a matrix times another matrix with the diagonal inside of it, that's going to take a form of the sum over, like the ijth entry of that is going to be basically just a weighted version of if we were to take the product of these two matrices. And since we're getting a path from one side and a path from this other side, we're going to define something like a composite object that's two paths together. So that's going to be called a track. So trek from xi to xj and g is a ordered tuple. I guess tuples are usually meant to be ordered, so it's a tuple, gamma 1, gamma 2 of paths, such that the thing that they're directed paths in particular, such that the gamma 1 path ends at xi. So we call that the sink of the path. The gamma 2 path ends at xj. And the paths have the same source nodes. They start at the same place. Okay. Let me give you some examples of this in the graph that we've defined over here. And we'll use these later. So let's say that my xi is this x3 variable, and my xj is the x5 variable. So one way to think about treks is that I'll go through all of the kind of possible sources for the trek. So if I have z1 as a source, what paths are there from z1 to x3? Well, in this case, there's just this one path, Z1 to Z2 to X3. So that gives me like the gamma 1 side of the track. And then there's 2 paths from Z1 to X5. There's Z1 goes to Z2, goes to Z3, goes to X5. And then there's the Z1 goes all the way to Z3, goes to X5. So that already gives me 2 tracks. So I have the track that involves these 4 edges, right? And then I have another track that involves this edge and this edge as the gamma 1 side. And then it involves this edge again on the gamma 2 side. So you're allowed to have you're allowed to have the same edge twice in tracks. They're just on different parts of the paths. And then there's another one, if you have Z2 as the source. So directly Z2 to X3, and then Z2 to Z3 to X5. Okay. And tracks are kind of exactly what we need to expand this out. In particular, this is going to give us that if we define this covariance matrix as sigma, then the ijth entry of that, it's essentially the same thing as we did when we were thinking about paths, where we kind of were summing over all the things that could have come in between. So it's all of the things that start at I and go to some node U. But since this is transpose, what it really is paths that start at U and go to I. And then this one is not transposed, so this is paths that start at U and go to J. So we kind of have like U on this side, and I and J, and we're summing over the entries in between, and then we get this weighted part that is the variance of that node. So in particular, one way to write this out would be the sum U equals 1 to D of sigma U squared. And then we're getting the IU entry of this. So this is the sum, as we said, over all paths from U to I because of the transpose. So this is paths XU, XI, the weight of that path, and then the weight of the gamma 2 paths, where these are paths from XU to XJ. Okay. If you don't want to write 3 summations, you can just write this. You can introduce new notation for all treks between Xi and Xj, and then you can just say, gamma 1, gamma 2 is a trek, and then just multiply these weights, and then that's weighted by the variance of the source node. Okay. So we're almost getting to using this for the DAG recovery. What does that tell us about the graph that we have here? So let's add those edge weights to it. So let's add, we have A13, A23, A12, and these are G's, because that was our mixing matrix. So we have G11, G12, G23, G24, G35, G36. So let's practice with the X3, X5 pair. Yeah. So the covariance of X3 and X5, we want to sum over all of the treks. So we said, okay, there's a trek. There's two treks starting at Z1. So one of those treks is going to give us A12 times G23. That's the weight of the gamma 1 path. And then the weight of the gamma 2 path, if we take this edge, is going to be A13 G35. And then we just have the variance of the source node. So that's sigma 1 squared. Similarly, the other one, same two guys there. But then we do A12, A23, G35, sigma 1 squared. And then the last one we said was from Z2. So that gives us G23, A23, G35. Sigma 2 squared. Okay. So that's the most complicated one that we're going to look at when trying to distinguish this model from the one that has the A13 edge missing. And I'll do this without complete motivation first, and then we'll come back and kind of discuss a little bit of how it's supposed to generalize. So the idea is that if we look at this model, and this is where it's important that we're in the noisy setting. So we're not in the deterministic G setting. We're doing X equals GZ plus some epsilon noise. What happens in that setting is that there are no conditional independences in this model if you can't condition on Z's. So you don't see the Z's. All you see are X1, X2, X3, X4. Like, even if you had no edge from Z1 to Z3, right, what that would imply in the model up here is that Z1 is independent of Z3 given Z2. But if we take the corresponding X variables, we don't have that X1, X2 is separated from X5, X6 given the X3, X4. Because we still have the path over here. We're not actually blocking it if these aren't deterministically related. But the models do differ. It's just that they differ in a way beyond conditional independences. So conditional independences, you can think of, as particular in the Gaussian case. We worked with, when we were doing the PC algorithm, we were doing like these transformations of the partial correlations, and that was because in the multivariate Gaussian case, zero partial correlation is like in one-to-one correspondence with conditional independence. But all we're doing, in some sense, is looking at kind of single entries of either the covariance matrix or kind of some conditional version of the covariance matrix. So what we're doing now is we're looking, you can kind of think of looking at single entries as looking at the determinants of 1x1 little submatrices. Trivially, just the determinant of a 1x1 submatrix is just that entry itself. What we're doing now is we're looking at the determinants of bigger submatrices. So what we're going to look at, you might remember that this showed up when we were looking at proxy variables, was the determinant of this 1, 3 by 4, 5. So this is a 2x2 determinant. And if we write out using the track rule these covariances, what we can see is that, okay, we are looking for paths between 1 and 4. Yes, okay. So between 1 and 4, the only way that we can get to both of them is starting at Z1 as the source. So in particular, we're going to have that term is going to be G11, G24, A12, sigma 1 squared. Right, this is from the first part. This is, it's in the opposite order of how I've been writing it over there, but it's from the second part. For the 1, 5 entry, we're going to have to start at Z1, but again, we're going to have 2 ways of getting there. So we're going to have, this is G11, G35, times A12, A23, plus A13 sigma 1 squared. This 3, 4 entry is going to be G23, G24, A12 squared. That's coming from the fact that we can use them multiple times, the edges multiple times. And then we already wrote out the other entry over there. So in general, this is a 2x2 matrix. It's going to have a rank 2. You can actually show if we have all of these entries, A12, A23, and A13, then this matrix is generically of rank 2. This is similar to our faithfulness assumptions, where we say, like, if we pick the parameters, like the set of parameters such that this matrix actually has rank 1 instead of rank 2 because of some like weird degenerate cancellations, like maybe like A13 being minus A12 times A23 or something like that, that is going to be of measure 0. So like generically, that's not what's going to happen. But in the case that we have A13 equals to 0, so we don't have it on this side, then I'll just replicate that equation without the, do we not have an A13 term? Should have. Oh, yeah. Yeah, we had it in the first term, right? Okay, so we would have A12. That's right, A12 squared, A23, G23, G35. This should be sigma 1 squared plus G23, G35, A23, sigma 2 squared. And we can actually factorize this, right? So look at the how much the second column is a multiple of the first column. So they share in common this A12 sigma 1 squared G11. And similarly, so this was like G3 times A23 times this column. So if we just leave out the G24 entry and look at these, we'll see that we have exactly the same thing replicated over here, except for the A23 and G35. So we're going to be able to factorize this into a column matrix times a row matrix. So this matrix is of rank 1. And that's exactly what's going to allow us to identify whether that edge is there or not. And kind of the direction that this is pointing in, which we don't have time to get fully into, is this generalization of D-separation. It's called Trek separation. And, you know, in D-separation we had one path, and then we had one set that told us whether or not that path was a deconnecting path. Now we're having a trek, which is two paths. We're going to have two sets that tell us whether or not this is trek separated or trek connected, I guess. So the definition of trek separation is going to say that we have sets A, B, SA, and SB. These don't need to be disjoint subsets, and we'll say SA, the tuple SA, SB, trek separates A and B if all treks from a node in A to a node in B, just say from A to B, have either that the gamma 1 path intersects with SA, or the gamma 2 path intersects with SB. So the result, which is the Trek separation theorem, says that the rank of a submatrix is less than or equal for any set that Trek separates them, the sum of the sizes of those sets. It actually says a little bit more, which is that if you do the minimum over all possible pairs of Trek separating sets, then this equality holds generically. And if we go back over here and we think about what happens when we remove the edge between Z1 and Z3, right, we were looking at the covariance matrix between X3, X5, and X1, X4. Then Z2 is like Z2 comma the empty set, Trex separates x3 and x5 from x1 and x4. So these are kind of the hard guys to separate. Once you put that in there, then any path from x1 to x3 has to go through there. Any path between those also has to go through there. And if you want to see how this kind of gets used, for latent DAG learning, the reference would be Silva's paper of 2006. And that's kind of, in some sense, what kicked off this latent DAG learning. A lot of people have been using kind of this pure child assumption, where you need to have, for each of the latent variables, at least some of the children to only depend on that latent variable. Now, when we're thinking of things like images, like that's kind of a no-go. Like you can't guarantee to me that like the top left pixel only depends on whether or not this thing's a dog or a cat or something. Like what, you know, I'm rotating the images. What if I get like the collar in there or the whiskers or like something like that? So this has been kind of motivation to go beyond these assumptions where we're restricting the sparsity on the mixing function. And as a trade-off, what we're going to have to do instead is add in data, and we're going to add in interventional data. Okay. Let me put up some of our facts from that part that are still going to be useful for us. So one of the expressions that we had was this guy. And then we said covariance of Z something that's kind of helpful has been to just collapse the all this into one matrix, not write it out all the way every time. So we'll have B equals I minus A transpose. Which way is it? We're going to do it like the inverse of this matrix. So we're going to have B is sigma to the minus 1/2 I minus A transpose. So this matrix will have no inverses in it. Right, and that's going to say then with this that the covariance is B inverse B inverse transpose. And then if we define the inverse of the covariance matrix, so we'll have that be theta is the covariance. Well, we want theta to be the inverse of the covariance of G, actually. So I'll just write it out. Covariance of Z inverse equals B transpose B. If this is a Gaussian distribution, this is referred to as like the precision matrix or the information matrix. I'm just using linearity here, so I'll just keep calling it the inverse covariance matrix, but that's a little connection in case y'all are interested. Right, and then if we have x equals g z, not plus any noise. So now we're going back into the deterministic setting. Okay, how does multiplication work with covariance? That turns into conjugation. So we would have the covariance of x equals g times the covariance of z, g transpose. And then if g is invertible, so if we want it to be invertible, we do need to have the same number of observed variables as latent variables. We have p equals to d. We'll work with this case now. Everything about this theory kind of goes through with p greater than d as long as g has full column rank. So it's like an injective linear function. And then in particular, this allows you to take the pseudo inverse, sometimes denoted by a plus or a dagger. But if we are just being simple for now and saying it's invertible, we'll just use G inverse, and we'll call that this capital H. So now the inverse of the covariance matrix for X is H transpose B transpose B H. And then I said what we're going to do is add interventions onto everything that we're discussing. And kind of the key thing is that we are intervening on the latent nodes, but the process that gets you from the latent nodes to the observed nodes, we're assuming stays constant across different interventions. So in particular, we're going to be indexing the interventions by k, so we can say like all of these are going to have like xk is going to be x. It's still a vector, but just in the kth context or intervention. So we can go through and add all of these. These g's stay the same, so they don't get a k subscript. Right? Neither does the h. And then what is an intervention? Well, in a linear model, if we're only intervening on a single node, right, we define this B in terms of the variances and the weight matrix. If we're intervening on a single node, that means we can change that node's variance, and we can change the weight of like all of the parents coming in. So in particular, we're just changing one row of B. So if we have like some base matrix, like B0 would be our observational setting. Then we're going to have BK is going to be B0 plus, if you want to do it this way, you could say there's going to be some place where we're intervening. That's going to be this IK variable. That's going to be the intervention target for the kth intervention. So we don't assume that we know the row that's being updated for each intervention ahead of time. And then this is times, so this is telling us to only affect the ikth row. And then this is telling us how we affect it. We're not going to do it in full generality. We'll just do the 2x2 case. So I'll write out all of these concretely. So we're going to have our observational matrix. So we're going to have B is going to be B11, B12, B22. We're going to have, let's make our indices letters, just so that we don't confuse, you know, we're not saying that like B, if I were to say B1, you might think, oh, that has to be an update to, you know, the first row or something. We just know that it is an update to a single row. We don't know which row that is. So in this case, let's say it's an update to the second row. So I've done an intervention on B22 and just changed its variance. So I get B22A, but the first row remains the same. And similarly, like this BB matrix will be an update to the first row. And we're going to be dealing with, if you remember our terminology for interventions, there is do interventions, which just set the value of like one of the z's. There were perfect interventions, which remove the dependence on the parents, but they still allow some variance of the node. So that's what's happening here. We're going to be working on perfect interventions. And then soft interventions would be if I replace this entry by like B12 superscript B. And it turns out you can't, in general, identify those models if you allow soft interventions in the latent space, at least from one intervention per latent node. You might need to be able to do it with multiple. So this is all like active research. Okay. Yeah, we have this set up. Now, what does that tell us about the covariance matrices for the z variables? So, no interventions. The inverse covariance matrix, we said it was B transpose B. This is for the z variable, so we don't have the h's in there yet. So this is B11 squared, B12, symmetric, so B11, B12, and then this is B12 squared plus B squared. And then we're going to get similar formulas for the inverse covariance in the B intervention and the A intervention. So in the B intervention, it actually is even simpler. We have this B11B squared, B22 squared. And then this one, we're just replacing one entry, the B22 entry here. So the idea behind this identifiability is to start looking at the differences between these. So we don't get to see the B's. We don't even get to see these. We get to see these after they're kind of conjugated by the H's. But when we do that conjugation, we're not changing the rank of anything. So in particular, when we subtract this from this one, the only thing that is left is this entry. So it's going to be a rank 1 matrix. And if we want to write it out fully, what we have is theta minus theta A. That's equal to H times, by linearity, just whatever is left when we subtract this guy from this guy. So we have 0, 0, 0, and then this is B22. Sorry, I missed some stuff. A squared, B22, A squared, which one did I write first? B22 squared minus B22A squared. H, this transpose. Right, so this is going to be a rank 1 matrix. And then when I subtract these two matrices, I'm going to get a rank 2 matrix. So I'm not going to write that out, but all of these entries are going to be still there. And that in general is going to kind of allow us to identify the intervention targets. So we know that we would only get a rank 1 matrix when we're intervening on, in this case, the way I've written it out is the more upstream variable. I think I switched between using upper and lower triangular. Okay, so that's not all it gives us. It's not just the intervention targets. It's not just telling us that this A intervention is on the more upstream variable. But then the idea is that if we look at the row span of this, so not just what's the rank of it, but what actual space do the vectors spanned by the rows of this matrix live in. Then that, because we're only multiplying by this, is going to be a multiple. It's basically going to be the span of the second row of H2, because we're doing the transpose. It's the row. And this is at least kind of partially getting us towards identifying the H matrix. So we don't know the scaling, but because of kind of overspecification of this problem, we don't really care about the scaling of the H's. Like if we have X, I guess if we have, we're saying Z equals H times X, we could just have some Z hat equals like lambda H X, where this is a diagonal matrix, and we just scale each of the Z hats compared to their original Z values accordingly. So actually this is good. This is kind of all we want. It's just that value of H up to like a constant multiple of the row of H to a constant multiple. And then the more complicated part is how to get the first row of H. So the idea there is to now look at the next difference. So this theta minus theta b. Again, as I was kind of saying, we're not doing anything nice with getting it low rank because of this middle matrix being rank 2. But what we can do is project this matrix, project both the row span and the column span of this matrix, now that we've recovered H2, onto the orthogonal complement of that. So this is basically, we have H1 and H2. If I project out onto the orthogonal complement, this row becomes 0, or this column becomes 0. And similarly over here, this row becomes 0. And I again get a matrix that's rank 1. And that now H1 might not be, I might have removed some of H2 when I did the orthogonal complement. So if I have Q1 is the projection of H1 onto this variable. What I'm kind of doing here is like a Gram-Schmidt orthogonalization of the rows of H. So I recover like this matrix Q1, H2 it's orthogonal. And I have to kind of get the part of Q1 that I left off. And that basically is going to come by taking this matrix, which is now, the way that I've done this is so that I can express the first row of H as a linear combination of Q1 and H2. So it's going to be some R11, R12, and then the second row of H is just a scaled version of this. So this is actually an upper triangular matrix. So if I call this R and I call this Q, what I've done is some kind of RQ decomposition of H. And then I can write out, okay, I have H transpose BK transpose BK H. That's what each of my theta k's are equal to. Now if I pre and post multiply by Q, so I know that this is equal to Q transpose R transpose BK transpose BK R BK RQ. If I pre and post multiply by Q transpose, these are orthogonal matrices. I just make a choice of when I was picking Q1, that choice is arbitrary, just make it unit length vector. And then, H2, I make a unit length vector. I guess really we should be calling this Q2. And then we pick Q1 orthogonal to that. So this is all going to cancel out. Then I'm going to get a product of a upper triangular matrix with itself. So this side's upper triangular, this side's lower triangular. That's the Cholesky decomposition of a matrix. And that's actually unique for a positive definite matrix, which theta k is. So I can actually recover the product BK times R, and kind of as a final step to recover the rows of R up to scalar multiple, which will then, combining R and Q, give me H. I can look at the difference between this BKR and this B0R, and just look at a single row of this matrix. Yeah, I'm not going to do this out, but this is in the notes. Okay. So that generalizes to arbitrary graphs in the latent space, and as I said, we can take P greater than or equal to D. There's also, so this is from a recent paper, there's also proof that, so you have to, basically for this proof to work out, you have to have one intervention per latent node. There's a proof that that's actually, in the worst case, necessary as well. So if you're missing an intervention on one of the latent nodes, you can have that your matrix H is actually not recoverable. And then there's some other papers out recently that also do this for 2 interventions. So this is Ahuja. As well as some papers that do something under soft interventions. This is super recent, so not sure about the details. And then something that I didn't talk about kind of at all in this lecture on causal representation learning, this would be the natural candidate, if we had another lecture on it, would be kind of this field of causality inspired representation learning, or ML. Which no longer makes the goal, kind of complete recovery of this latent DAG, but maybe just, the predictors for some outcome variable that you care about. So that is, I guess, the citation I would start with and look at some of the works from there. This is Grajowski 2019. Then there's a nice, I think it's a 2021 review by Shulkin Fidel.